Fermat's little theorem. Before we discuss Fermat's little theorem, let me go back. Let me go back to this section, mathematical induction. Please take a look at the following set of problems. In example 9, we proved that 3 divides n cubed minus n for any integer n. In number 10, we proved that 5 divides n to 5th power minus n. In 11, we proved that 7 divides n to 7th power minus n. Note that when we increase the power, our computations become more and more complicated. Now, looking at these 3 examples, one can come up with the following conjecture. P divides n to p minus n for any integer n, where p is a prime number. This is true, but it is not that easy to use induction to prove it. Because if you replace 7 by p everywhere, over here, you'll get k plus minus 1 to p's power. And then if you expand parentheses here, you will get binomial coefficients. Therefore, the next step would be to prove that each binomial coefficient here is divisible by p. How would you prove it? It's not that easy. If we have a particular value of p, and if p is small, we can just check. But what if p is large, or we have some p? How to prove that each coefficient here is divisible by p? It's a good question. So, over here, we prove the following. P divides a to p minus 1 if a is not divisible by p. And then, later, as a corollary, we will prove the following. P divides a to p minus a, where p is prime and a is a positive integer. Note that what we discussed here, this, and this, are particular cases of this. So once again, in order to prove it, we need Fermat's little theorem. Fermat's little theorem says the following. If p is prime and a is an integer such that a is not divisible by p, then p divides a to p minus 1 or equivalently a to p minus 1 is congruent to 1 modulo p. Now let us discuss 3 remarks. Remark number 1. This condition is important. Indeed, if p divides a, then this, and therefore this, is not true. Here is why. If p divides a, this means a is congruent to 0 modulo p. Now let us raise both sides to the power p minus 1. A to p minus 1 is this, 0 to p minus 1 is 0. Conclusion, if p divides a to p minus 1 is congruent to 0. Since a to p minus 1 is congruent to 0, it is not congruent to 1 modulo p. Any questions about remark number 1?
I think I get it, but why do we know immediately that if a to the power p minus 1 is congruent to 0, then it's not congruent to 1?
Because by division algorithm, a remainder is unique. If we divide this by p, the remainder is 0. This means the following: if we divide this by p, the remainder is 1. But the remainder is unique, we got a contradiction. You see it?
Yes.
Next, a remark number 2. This condition is also important. For example, if a is equal to 2 and p is 9, p is not a prime number. Then a to p minus 1 is 255. This number is not divisible by 9. However, please take a look at this word, in general. We put here in general because sometimes p is not prime, but this is true. Here is an example. Note that 4 is not a prime number. Nevertheless, 5 to 4 minus 1 is congruent to 1 modulo 4. By the way, if a is equal to 2, it's significantly harder to find such an example. One can show that the lowest positive integer, such that this integer is not prime, but this is true, is 341. 2 to this power is congruent to 1 modulo p, but p is not prime. So once again, if we combine a remark 2 and a remark 3, we conclude the following. Sometimes p is not prime, and this is true. Sometimes p is not prime, and this is not true. So for some composite numbers, this is true. For some composite numbers, this is not true for certain values of a. For example, once again, here p is composite and this is not divisible by this. Over here, p is composite, but a to p minus 1 is congruent to 1 modulo p. In short, both conditions, this and this, are indeed important. We cannot skip this, we cannot skip this. Now let us discuss the proof. Here's what we do. So we start with an integer such that a is not divisible by p. Here is what we do next. Let us multiply this a by the following numbers: 1, 2, 3, and so on p minus 1. Let us consider the following numbers: a, 2a, 3a, and so on p minus 1a. Here's what we do next. Let us divide each of these numbers by p. By the division algorithm, we have a is equal to pk1 plus r1, 2a is equal to pk2 plus r2, 3a is equal to pk3 plus r3, and so on. P minus 1 times a is equal to p times k p minus 1 plus r p minus 1. Here's what we do next. Let us go back to one of our previous sections over here, Introduction to Congruences. Please take a look at Theorem 1. Theorem 1 says the following. A is congruent to B modulo M if and only if there is an integer k such that A is equal to B plus km. This is exactly how we jump from here to here. So once again, since this implies this, this implies this, this implies this, and so on.
Wait, so why? How come it's not by definition?
Well, here's why. Note that by definition, A is congruent to B modulo M if M divides A minus B. This is the definition.
Okay, I see.
Here's what we do next. Let us go back to section 4.1 again. Please take a look at Theorem 4. Theorem 4 says that if we have two congruences, we can multiply the left-hand sides and the right-hand sides. Done. This is exactly what we do next. Let us multiply out all these congruences. As the result, on the left-hand side, we will get the following. A times 2A times 3A times and so on, P minus 1 times A. Note that over here we have P minus 1 congruences. Therefore, the product of all left-hand sides will be A to the power P minus 1 times 1 times 2 times 3 times and so on times P minus 1. And note that 1 times 2 times 3 times P minus 1 is P minus 1 factorial. Therefore, the product of all left-hand sides is A to the power P minus 1 times P minus 1 factorial. It's exactly what we have here. Of course, the product of right-hand sides is R1 times R2 times R3 times and so on times R P minus 1. It's exactly what we have here. The goal of the next step is to show that this product is actually equal to P minus 1 factorial. After that, we will cancel out P minus 1 factorial and get the desired result. But we have to do all these steps carefully. So let us do it slowly. Please take a look first at what is written here. Observation number 1. Ri's, all these Ri's, R1, R2, R3, and so on are between 0 and P minus 1. Folks, who can tell me why Ri is between 0 and P minus 1? Why is that?
Is that not by definition of the division algorithm?
By division algorithm, absolutely. By the division algorithm, all our remainders are greater or equal to 0 and lesser or equal to P minus 1. So this is by the division algorithm. Next, note that any Ri is not equal to 0. Indeed, assume to the contrary that some Ri is equal to 0. If sum Ri is equal to 0, this means P divides IA. For example, if R1 is equal to 0, A is equal to PK1 means A is divisible by B. If R2 is equal to 0, 2A is equal to PK2 means 2A is divisible by P. If R3 is equal to 0, 3A is equal to PK3 means 3A is divisible by P. In general, if Ri is equal to 0, IA is equal to PKI, which means IA is divisible by P. It's exactly what is written here. So, P divides the product of two integers, I and A. Now let us go back to Theorem 2 from section 3.5. Please take a look at the following. Over here, Theorem 2 says the following. If P divides the product, P divides one of the factors. This is exactly what we have here. P divides the product, therefore either P divides I or P divides A. Note that this is impossible. Here's why. Remember, P is greater than I. So P cannot divide I. Moreover, at the very beginning, we assumed that P does not divide A. It's written here. Over here, this is our assumption. Therefore, this is impossible. So, this is impossible. This is impossible, therefore this is impossible, therefore Ri is not equal to 0. So, over here it's written Ri is greater or equal to 0, lesser or equal to P minus 1. But since Ri is not equal to 0, Ri is greater or equal to 1. And lesser or equal to P minus 1. Next. So, as we discussed, if we multiply out all these congruences, we get this. Now, lemma. We prove that this product, which is over here, is equal to P minus 1 factorial. In order to prove that this is equal to this, first let us show that all these R's are distinct. We will prove it by contradiction. Assume to the contrary that Ri is equal to Rj for some I not equal to j. Here is what we do next. Let us go back to 3. Note that according to what is written over here, this portion, if Ri is equal to Rj, since Ri is Ia minus Pki, and since Rj is Ja minus Pkj, Ia minus Pki is equal to Ja minus Pkj. So this implies this by this. Here is what we do next. Let us move this to the left and this to the right. After that, factor out A on the left and factor out P on the right. We get this. Now, since Ki minus Kj is an integer, the right-hand side is P times an integer number, which means the left-hand side, by definition of divisibility, is divisible by P. It's exactly what is written here. P divides the left-hand side over here. And now again, let us use Theorem 2 from section 3.5. This theorem: if P divides the product, P divides one of the factors. So P divides the product, therefore P divides either this or this. It's written over here, either P divides I minus J or P divides A. Note that this is impossible because P is greater than I, P is greater than J, therefore P is greater than I minus J. Remember, I is between 1 and P minus 1. Therefore, of course, J is between 1 and P minus 1. So both I and J are lesser than P. Therefore, I minus J is lesser than P. Similarly, as we discussed, this is impossible because at the very beginning we assume that P does not divide A. So this is impossible, this is impossible, therefore P does not divide this, therefore this is impossible, this is impossible, therefore this is impossible. So all these numbers are indeed distinct. Here's what we do next. Note that any of these numbers is between 1 and P minus 1. These are distinct integers, and there are exactly P minus 1 integers here. So we have P minus 1 distinct integers that are between 1 and P minus 1. Therefore, the set of these integers is equal to the following set: 1, 2, and so on, P minus 1, which means the product of these numbers is equal to the product of these numbers, which is P minus 1 factorial. Proven. Here's what we do next. By this lemma, this product, which is over here, is equal to P minus 1 factorial. So if we replace this by this, we get this. Here is what we do next. Let us go back to corollary 1 to theorem 7. Here it is. Corollary 1 says the following. If we have the following congruence, AC is congruent to BC modulo M, and if C and M are relatively prime, then C can be cancelled. So this implies this. Moreover, it's if and only if statement, but what we need in our case is the following. C can be cancelled if C and M are relatively prime. Note that since P is a prime number, P P is a relatively prime with any number from the set, with 1, with 2, and so on with P minus 1. Therefore, since P is a relatively prime with P minus 1, P minus 1 can be cancelled. Since P is a relatively prime with P minus 2, P minus 2 can be cancelled, and so on. Since P is a relatively prime with 2, 2 can be cancelled. If we cancel all these numbers, this becomes this, which is exactly what we need. The theorem is proven. Next, corollary. If P is prime and A is a positive integer, then P divides A to P minus A, or equivalently, A to P is congruent to A modulo P. Please compare this corollary with Theorem 2. In Theorem 2, P does not divide A. Over here, there is no such a condition anymore. Difference number 2. Over here, we say that P divides A to P minus 1 minus 1. Over here, we say P divides A to P minus A. So there are two differences. Number 1, we skip the requirement A is not divisible by P. Difference number 2, instead of A to P minus 1, we have A to P minus A. How do we prove it? Here's what we do. Suppose P does not divide A. If P does not divide A, we can use Fermat's little theorem. By Fermat's little theorem, A to P minus 1 is congruent to 1 modulo P. Now, we multiply both sides by A, and the desired result follows. Case 2. Suppose P divides A. If P divides A, of course, P divides A to P's power. This means A is congruent to 0 modulo P. It's exactly what is written here. This means A to P is congruent to 0 modulo P. Since both A to P and A are congruent to 0 modulo P, A to P is congruent to A. And we get the same result again. Folks, any questions here?
Yeah, I have a question. What's the point of the part of the proof that says if P divides A, then P divides A to the P as well? Haven't you already finished it once you multiply the A to the P minus 1 congruent to 1? When you multiply both sides of that by A, isn't it done right there?
Excellent point. Note that we have this only if P does not divide A.
Oh, yeah.
So the proof consists of two parts. Part number 1, suppose P does not divide A. Part number 2, suppose P divides A. In case number 1 and case number 2, we deduce this in two fundamentally different ways. Does this answer your question?
Yeah, it does.
Why wouldn't this work if P was composite?
Because in this case, we have to use Fermat's little theorem. However, as we discussed, please take a look at this remark. If P is not prime, then in general, this is not divisible by P. Here is an example. A is equal to 2, P is equal to 9. A 2P minus 1 is 255, which is not divisible by 9. Does this answer your question?
Yes, thanks.
Now, let us talk about applications. Let us go back to section 1.3, math induction. Remember, it took quite some time to prove this, and then this, and then this. Note that all three examples follow from what is written here. Now let us discuss other examples. Let us prove that 17 divides a to the power at minus 1, where a is a positive integer which is relatively prime with 17. Observe that we cannot apply Fermat's little theorem directly, because by Fermat's little theorem, 17 divides a to 16th power minus 1. This is not 16, this is 80. But Fermat's little theorem is a good starting point. So once again, since a and 17 are relatively prime, by Fermat's little theorem, a to 16th power is congruent to 1 modulo 17. Here's what we do next. Let us go back to section 4.1. Please take a look at theorem 5. If a is congruent to b modulo m, a to kth power is congruent to b to kth power modulo m. This is exactly how we jump from here to here. We raise both sides to 5th power. 16 times 5 is 80. 1 to 5th power is 1. So this is congruent to this modulo 17, means 17 divides a to 80th power minus 1. We are done. Folks, any questions here?
Why is it significant to state that a and 17 are relatively prime?
Another excellent question. Remember, in order to prove this, we have to use Fermat's little theorem. However, in Fermat's little theorem, we say that P does not divide A, which means P and A are relatively prime, because P is a prime number. Next. Please take a look at this example. Again, A and 23 are relatively prime. We want to prove that 23 divides A to the power 154 minus 1. Since A and 23 are relatively prime, and since 23 is a prime number, we can use Fermat's little theorem. By Fermat's little theorem, A to the power p minus 1, p is 23, 23 minus 1 is 22. A to the power p minus 1 is congruent to 1 modulo p. And then, by theorem 5, we can erase both sides to the power k. It's exactly how we jump from here to here. We can erase both sides to 7th power. And the result follows, because 22 times 7 is 154. But now we have a hard example. Prove that 300 divides 11 to 10th power minus 1. Note that we cannot apply Fermat's little theorem directly because 300 is not a prime number. So what do? Folks, any ideas here? How can we prove it?
Can we first start by proving that 3 doesn't divide that?
Does not, you said does not.
Sorry, that it does divide.
Okay, excellent. We can prove that 3 divides this. How can we prove it?
Using Fermat's little theorem?
Using Fermat's little theorem. 3 is a prime number. Guys, indeed, in order to prove that 300 divides this, let us prove that 3 divides this. We will do it at the very end of the proof. Right now, let us show that what is written here is divisible by 100. Here is how we do it. Note that 100 is 2 times 10 times 5. First, let us show that this is divisible by 5. In order to show that this is divisible by 5, let us factor this out. Here is what we do next. Let us think about 11 as about A and 1 as about B. A 2/5 power minus B 2/5 power is A minus B times A 2/4 power plus A cube plus A square plus A plus 1. Let us show that this is divisible by 5. Well, easy way to show it is the following. Note that if we raise 11 to 4th power, the last digit will be 1. Similarly, the last digit is 1, the last digit is 1, the last digit is 1, and here 1. If we add 5 numbers, and if in each case the last digit is 1, the last digit of the whole sum is 5. So this number is divisible by 5. Here's another way to prove it. Obviously, 11 is congruent to 1 modulo 10. If we raise both sides to nth power, we get this. So each of these numbers, according to what is written here, is congruent to 1 modulo 10. And now let us add up all these congruences. For n is equal to 4, 3, 2, 1, and 0. We will get this. And now, since 5 is divisible by 5 and 10 is divisible by 5, this is divisible by 5. Next, note that this odd plus odd, even, this is divisible by 2. Lastly, 11 minus 1 is 10, divisible by 10. So in total, this is divisible by 5, this is divisible by 10, this is divisible by 2. Therefore, in total, the whole product is divisible by 2 times 10 times 5, which is 100. Lastly, by Fermat's little theorem, this number is divisible by 3 because 11 square minus 1 is divisible by 3, means 11 square is congruent to 1 modulo 3. And if we raise both sides of this congruence to 5th power, we will get 11 to 10th power is congruent to 1 modulo 3. Means 11 to 10th power minus 1 is divisible by 3. Now let us put pieces together. This is divisible by 100. This is divisible by 3. Since 3 and 100 are relatively prime, the whole expression is divisible by 300 by this corollary from section 3.5. In section 3.5, we proved that if C is divisible by A and is divisible by B, it is divisible by its product if A and B are relatively prime. Next, please take a look at this. What is the remainder after dividing 3 to 50th power by 7? Again, we use Fermat's little theorem. Since 7 is a prime number, and since 3 is not divisible by 7, by Fermat's little theorem, 3 to the power p minus 1, which is 6, is congruent to 1 modulo 7. Here's what we do next. Let us raise both sides to 8th power. Done. Conclusion. 3 to the power 48 is congruent to 1 modulo 7. But we need 3 to the power 50. What do we do? Well, just multiply both sides here by 3 square, by 9. If we multiply the left-hand side by 3 square, we get this. If we multiply the right-hand side by 3 square, we get this. Lastly, observe that 9 is congruent to 2 modulo 7, therefore the remainder is 2. Next, Theorem 3. Theorem 3 says the following. If P is prime and A is an integer such that P does not divide A, then A to the power P minus 2 is an inverse of A modulo P. So, first of all, let us talk about the following. Let me remind you what is inverse. Again, let us go back to one of our previous handouts. In simple words, inverse of A modulo M is a solution of this congruence. Here, Theorem 3 says the following. Let us consider the following congruence. AX is congruent to 1 modulo P. Then A to P minus 2 is a solution of this congruence. Why is that? Since P does not divide A, it's written here. By Fermat's little theorem, we have the following. A to P minus 1 is congruent to 1 modulo P. Note that A to P minus 1 can be rewritten as A times A to P minus 2, which means A to P minus 2 is a solution of this congruence. We just replace x by a 2p minus 2. Therefore, by definition of inverse, a 2p minus 2 is an inverse of a modulo p. Next, let us go back to section 4.2 again. Remember, in this section, we discussed the following corollary. If A and M are relatively prime, in order to find a solution of this congruence, we do the following. Step 1, we solve this congruence as is a solution of this congruence, and then x in solution of this congruence is congruent to bs modulo m. In short, in order to solve this congruence, first we find inverse of a modulo m and then multiply b by this inverse. But remember, we just discussed by theorem 3, inverse of a modulo p is a 2p minus 2. So we get the following result. Let a and b are positive integers and p be a prime number such that p does not divide a. Then the solutions of the linear congruence ax is congruent to b modulo p are the integers that are congruent to a 2p minus 2 times b modulo p. Because according to theorem 3, s is a 2p minus 2. So here's proof. Suppose ax is congruent to b modulo p. Since p does not divide a, by the theorem above, this is an inverse of a modulo p. Now, just multiply both sides here by this, we get this. And now note that what is written here is a to the power p minus 1. By Fermat's little theorem, a to p minus 1 is congruent to 1. So this is congruent to x. Therefore, x is congruent to this. We are done. Here's an application. Find all solutions of this congruence. There are two solutions here. Solution number 1 is from section 4.2. But please take a look at solution number 2. Since p is a prime number, and since p does not divide 2, we can apply the corollary above. By the corollary above, a is congruent to a 2p minus 2 times b. It's exactly what is written here. But now, in our case, a is equal to 2, p is equal to 7, and b is equal to 5. In total, we have 160. 160 is congruent to 6 modulo 7. So either we use section 4.2 approach or we use the corollary above.